Why is there more matter than antimatter in the universe? Now, you might not have ever asked yourself about why there's more matter than antimatter in the universe, or if it has occurred to you, you might think this is something in the realms of science fiction. Well, put that thought away, because this is one of the most profound mysteries in particle physics. We don't know why there's so much matter in the universe, but we want to understand it because it will be the only way to understand our place in the universe and ultimately why we exist. But before I get into our measurement, let me give you some context. So we know the universe is made of matter, and we know that matter is made of fundamental particles. Every type of fundamental particle that we know of potentially has an antimatter equivalent, a particle that has the opposite charge, that behaves like a mirror version under one of the fundamental forces, the weak force. Now, at the time of the Big Bang, we think that half the universe started off as made of matter and half antimatter. But in the universe today, there's very little antimatter around. There's some antimatter that's made by natural processes, for example, the radioactive decay of potassium in bananas, and some that's generated by artificial processes inside particle colliders, like the Large Hadron Collider, or inside PET scanners. But the total amount of antimatter is minuscule compared to the amount of matter. So how do you lose half a universe's worth of antimatter? Well, we think the answer lies with what went on in the very first moments of the universe. Here, fundamental particles met antiparticles, they annihilated, releasing photons that then, provided they had enough energy, created new particles and antiparticles in turn. And this cycle of annihilation and creation continued as the universe expanded. However, as the universe expanded, it also cooled down, and everything in it slowed down and lost energy. Until eventually, maybe less than a second after the Big Bang, everything had lost so much energy and slowed down so much that these annihilations no longer had enough energy in the photons to make more particles and antiparticles, and the whole process stopped. Now, what remains in the universe today is made of the leftovers of those last annihilations. And the fact that we're here, made of matter, means that there must have been very slightly more matter than antimatter at that point. Otherwise, we wouldn't be around. So if we want to know exactly how we got here, we'd better understand what made antimatter that little bit different to normal matter. Perhaps it decays faster. We don't know. Now, we call this difference in behavior between matter and antimatter CP violation, and that's because to turn matter into its antimatter equivalent, or vice versa, you change its charge, C, and you make it behave like a mirror version of itself, which is a parity transformation, or P. And the fact that matter and antimatter don't behave identically means that the symmetry between them is broken, and thus CP is violated. Now, we don't know why CP violation occurs, but we know it does. We discovered this experimentally back in 1964 when we were studying strange quarks. And since then, experiments have built up a huge body of evidence to show that there's also CP violation in bottom quarks as well. And then, very recently, LHCb has added to that knowledge by making the first observation of CP violation in charm quarks, a whole new fundamental particle species. Now, LHCb can do this because when the Large Hadron Collider collides its beams inside the experiment, it creates huge data sets of quarks and antiquarks, giving us both to study. And LHCb, to study charm CP violation, looked for evidence in LHC collisions of particles called d mesons. These are particles that contain charm quarks. However, they're unstable particles, and they only exist for about 10 to the power minus 13th of a second after they've been produced, before they decay to other things. As a result, LHCb can't see them directly, but it can detect them by finding the characteristic experimental signature d mesons leave behind when they decay. So we've sifted through our data set, our entire data set up to the end of 2018 to count how many d mesons we can find in this time. And then, looking at those d mesons, we can tell which ones are made of matter and which ones are made of antimatter. If we compare that ratio of matter to antimatter to the ratio that we believe was produced in the LHC in the collisions originally, about half-half, we can see if any CP violation has occurred. And in fact, that's what we do see. We see a small but distinct domination of matter over antimatter. There is a small amount of CP violation exhibited by charm quarks. Now, this is really important. And it's important because up to now, the difference in behavior we've seen in matter and antimatter in quarks isn't big enough to explain to us how the universe can evolve from the Big Bang to today. It just isn't. And we've been thinking that the answer to this mystery must lie in the behavior of particles we have yet to discover in the universe, whose difference between matter and antimatter can fill the gap that we're missing. Now, we've seen an extra source of CP violation in charm quarks. It's not sufficient to fill that gap because it's only tiny. But the excitement comes because it provides us with a whole new laboratory to study CP violation effects, and in particular to study CP violation in charm to see if we can detect the influences of any of these new particles that we think might hold the answer. So in a sense, although we've made this observation, it's just the start of the story. We've proved we can do it. We've proved we can study this system. Now we're going to collect the rest of the data that the LHC is going to deliver and study that in detail to see what else it can tell us. And then hopefully we'll have learnt more about why we exist and why our universe is made of matter rather than antimatter.